So good afternoon, everyone. It's a pleasure to have you all to see the PhD defense of my student Mileni Isikawa. Uh, I'd like to acknowledge the members of this committee. So Professor Roger and Mauricio, both from University of São Paulo, and Professor Ross from Harvard Medical School. So Millennium will have between 40 to 60 minutes to present her results. And after that we're gonna have the time for the committee to ask and to discuss the results. So thank you all for accepting this invitation, and Mileni, you can start your presentation.
However, I observe in many papers, it's reported the use of high atomic number nanoparticles in radiotherapy conditions improve ROS production in some cases up to threefold, suggesting that chemical pathway may play a major role in radiosensitization process. So in this work, our strategy is produce nanoparticles that actively produce reactive oxygen species under X-ray radiation. And to understand how this radiosensitizer works, I would like to present some possible radiosensitizers. So, as I mentioned before, the classical approach is the high atomic number materials such as gold or bismuth developed, characterized, and evaluated nanocenter, capable of enhancing radiation-induced cytotoxicity using and generation using two mechanisms. One of them is a scintillation-mediated XPDT, and X-ray, and second is X-ray treated release of stored singlet oxygen. Okay, following the concept of radiation activated in platform, we developed and published in last year hybrid nanoparticles with European doped gadolinium fluoride conjugated with methylene group to X-ray activated photodynamic therapy. And to understand how this system works, I would like to present review of photodynamic process and some main limitations. So photodynamic therapy or PDT is a minimally invasive therapeutic modality. Relies three components, photosensitizers, light with appropriate wavelength, usually UV or visible near-infrared light, and molecular oxygen. So PDT works when photosensitized absorb light and becomes excited state in this singlet excited state. In this singlet state, photosensitizers may intersystem crossing and become triplet state. And the photosensitized triplet state can transfer energy or transfer electrons and generate reactive oxygen species. And these ROS are ultimately responsible for inducing oxidative damage and cell death. PDT has a spatial and temporal control with systemic toxicity. However, PDT is strongly limited by the shallow penetration of visible and near-infrared light in biological tissue, which becomes a challenge in deep-seated tumor. So this limitation motivated the development of alternative strategies to access these deep-seated tumors. And one of the strategy is an X-ray activated photodynamic therapy or XPDT. Here, XPDT replaces optical station to X-ray radiation, and XPDT has a synergetic toxicity from direct radiation-induced DNA damage and local dynamic oxidative stress. However, a direct X-ray station of photosensitized is inefficient because photosensitized have extremely low X-ray absorption which motivated uses scintillator nanoparticle as an energy injector. And how this system works. Scintillation nanoparticles can absorb X-ray through photoelectric or quantum interaction and emit UV visible photons. These photons locally activate photosensitizers and photodynamic process happens. So using combination of scintillator material with photosensitizer, we can deep tissue photodynamic activation. And these scintillation materials need some features. One of them is a strong X-ray absorption. Another is a high scintillation intensity and a combination of scintillation with absorption of photosensitizers. And we choose europium gadolinium fluoride nanoparticle as our scintillation nanoparticles and methylene blue as our photosensitizers because gadolinium has a high atomic number, which improves X-ray absorption. Additionally, the presence of gadolinium also opens a possibility of MRI contrast applications. And europium has a red emission around 610 nanometers, which overlaps with methylene blue absorption, as you can see here in figure. In black line is a europium emission, in blue line is a methylene blue absorption. And europium has a similar uniformity, allows the doping process. So to produce this hybrid system, first I need to synthesize the europium doped gadolinium fluoride nanoparticle or GDF nanoparticle. For this, I choose microfluidic approach. So first, I mixture gadolinium and europium precursors in ethylene glycol and the gas, and then inject ammonium fluoride to start nucleation. Then I transfer the solution to microfluidic reactor where I control the temperature and residence time. This nanoparticle is characterized using structural, morphological, and optical techniques. So once I synthesize GDF nanoparticles, next I need to conjugate GDF with methylene blue. For this, I choose electrostatic layer by layer assembly because GDF, the methylene blue, has a positive charge, so interaction between these two materials is inefficient. So I used polyacrylic acid or PAA to change GDF surface surface charge to negative, and then conjugated with methylene blue. One PAA methylene blue conjugation is defined as 1B, and I repeat this process several times to ensure all surface coverage. And as you can see here in figure, with the position process, I increased blue color intensity in nanoparticles. And to measure singlet oxygen, I perform ESR spectroscopy with TPC trap. So when TPC interacts with singlet oxygen, nitrogen bonds changing and appear ESR signal with these three peaks. I mentioned peak-to-peak intensity in dark controls, which means without X-ray radiation, and the X-ray radiated samples. And I evaluate cytotoxicity of nanoparticles using MTT assays and chromogenic assays. So now here is the results of GDF characterization. Immediately after synthesis, I process nanoparticle with home shapes and average size of 10 nanometers. And 1 week after synthesis, these nanoparticles self-assembly and form flower-like nanoparticles and increase size to 40 nanometers. Hydrodynamic size was measured during 5 months and remains stable. And XRD analysis showed orgone crystallization, and the radioluminescence spectra shows the europium emission, which suggests successful doping of europium in GDF hosts. So next is results of conjugation process. So for 10 images, we can observe a formation of thin organic shells surrounding of GDF nanoparticles. And the ALS measurement shows the increase in hydrodynamic size with the conjugation process. Before conjugation, I have a nanoparticle with hydrodynamic size around 40 nanometers, and after conjugation process, nanoparticles increase size to 100 nanometers. And radioluminescence progressively increase as a number of time of the deposition process, indicating strong interaction between methylene blue and yellow. And to access energy transfer process, I evaluate in time resolved photoluminescence measurements. So bare nanoparticles and bare nanoparticle with solution of methylene blue without conjugation process. Lifetime is around 4.8 milliseconds, which means the interaction of GDF nanoparticle with methylene blue solution, we don't observe the energy transfer. However, when we have a conjugation process, the lifetime decreased to 0.1 milliseconds, indicating that efficient resonance energy transfer between europium and methylene blue. And here is a result for singlet oxygen measurement using ESR spectroscopy. So I observed strong ESR intensity for at 48 gauge source, where photoelectric effect enhances X-ray absorption from gadolinium. And when I increase X-ray energy source, I observed a decrease in ESR intensity. However, still high energy source such as calcium, I observed twofold decrease in ESR intensity compared to the nanoparticle without X-ray radiation, suggesting that activity under clinically relevant conditions. And here, results of dose-dependent experiment, and I observed for GDF with methylene nanoparticles produce significantly more singlet oxygen compared to the control group. Here, this control is bare nanoparticles, and I observed increase linearly with dose. And here in cytotoxicity results, I evaluated MTT assays for two cell lines, A549 and LLC cells. And for in A549 cells, both nanoparticles, bare nanoparticles and nanoparticles with methylene blue, showed low toxicity. In contrast, for LLC cells, I observed more toxicity for GDF with methylene blue nanoparticles, suggesting difference in oxidative stress response. And for radiosensitization, to access radiosensitization, I evaluated clonogenic assays using A549 cells. And for plates without X-ray radiation, I don't observe any difference between the controls and GDF with methylene blue, suggesting that GDF with methylene blue no significant toxicity. And when I observed plates for X-ray radiated and GDF with methylene blue cells treated, we observed the lowest colony survival. And this is translates to the survival fraction curve, where here is evaluating different doses, and we can observe for GDF, where GDF nanoparticles has a low survival fraction curve compared to the control. Here, this control is cells without any nanoparticles, any treatment. So here, expected enhanced local dose position for gadolinium, and GDF methylene treated cells show the lowest survival fraction curve, suggesting that dual mechanism of radiosensitization, combining high atomic number enhancement to the high atomic number dose enhancement and the scintillation mediated singlet oxygen generation. So partial conclusion of this first approach, I successfully synthesized GDF nanoparticle using microfluidic approach with successful conjugate process. Then we measure oxygen generation and the X-ray radiation, suggesting that efficient scintillation mediated energy transfer. And I mentioned singlet oxygen production at high beam energies and dose-dependent radiosensitization behavior. So this GDF nanoparticle has a potential reduction of therapeutic doses. However, this system still depends on oxygen availability. Since photodynamic process, photodynamic activation requires molecular oxygen to generate singlet oxygen, which becomes challenging in more hypoxic region. This challenge motivated the second part of this work. Here, the strategy was produce nanosystem capable of storing and release reactive oxygen species and the release of reactive oxygen species. This investigation results in one paper published in other reviews. And to understand how this system works, I'd like to use polycyclic aromatic hydrocarbon, or PAH molecule, has a pi conjugated aromatic rings, and the PAH is the one classes of molecule capable of storing and releasing singlet oxygen under controlled manner. One specific PAH molecule is anthracene, which is the focus of this work. Anthracene has three fused aromatic rings, and when anthracene interacts with singlet oxygen through 4+2 cycle additions, singlet oxygen is trapped in centered aromatic rings of anthracene and forming a superoxide or EPO structure. This EPO, under external stimulus such as thermal, chemical, or photophysical, can release singlet oxygen through cycle reversion process with regenerated anthracene and the release singlet oxygen. And our strategy in this work explores the possibility of X-ray as a trigger to release singlet oxygen. And to perform this, we need to synthesize anthracene PO. However, anthracene is a high hydrophobic materials in aqueous environment, so forming the micrometric clusters with poor solubility, low colloidal stability, and the results restricted cellular uptake. So we choose choose to conjugate gold nanoparticle, metal nanoparticle with anthracene to prevent disaggregation, because metal nanoparticle acts as a structural scaffold, and we which preserves nanoscale and improves colloidal stability in aqueous environment. Additionally, uses of metal nanoparticles with high atomic number is particularly desirable for our aim to X-ray trigger singlet oxygen. And to perform this hybrid system, first I need to synthesize gold nanoparticles and silver nanoparticles, and I use a chemical reduction methodology. In this, for these gold nanoparticles, gold precursor was mixed with sodium boride in presence of PVA as stabilizers, and followed by dialysis to ensure colloidal purity. And the silver nanoparticles, from silver nanoparticles, I changed the silver precursors. And synthesize hybrid system, gold system or silver system. I use a sonochemical approach. So gold nanoparticles or silver nanoparticle solution was mixed with ethanol anthracene solution in ultrafine depth, and these nanoparticles was characterized using structure and using morphological and optical techniques. And to track singlet oxygen in hybrid structure, I choose methylene blue with radiolyte irradiation as a singlet oxygen generator source, and I mentioned fluorescence. And the singlet oxygen release was measured using ESR spectroscopy with TPC spectrography. And finally, to evaluate cytotoxicity of the system, I use a confocal microscopy, self-update studies, MTTSAs, and chronogenic assays. And here, roots of golden nanoparticle characterization. So to synthesize golden nanoparticles, I use an 8-fold higher precursor concentration and sodium boride as a strong reducing agent. So with this strategy, I promote fast nucleation and reduce and limited particle growth. With this, I process a particle with size around 4 nanometers. For HR10 image, we can observe spherical nanoparticles with monodisperse and monodisperse. And the UV visible absorption spectrums shows the one plasma resonance peak centered at 534 nanometers, consists with spherical, well-dispersed golden nanoparticles. So then, gold nanoparticle synthesize, I synthesize hybrid structure. So here is the result of this characterization. When I try to synthesize bare anthracene nanoparticles, I produce large aggregates with size of around 700 nanometers. And when I use metal core, I decrease this size to nanoscale. And in particular, for gold with 1 anthracene and gold with 3 anthracene, here I change the amount of anthracene during the synthesis to evaluate how this influences in size. And when I choose 1 to 3 anthracene, I process nanoparticle with sizes below 10 nanometer, which is particularly desirable for biomedical applications. Mental enhanced fluorescence show up to a 9-fold increase in the strong interaction between the gold core, the metal core, with anthracene organic shells. And atomic first microscopy phases image shows the 2 domains. One corresponds to the metal core, and another corresponds to organic shells of anthracene. So these results suggesting that successful core shell formation of gold with anthracene. After synthesize a hybrid structure, I trapped singlet oxygen in gold with ultrasound. And to evaluate this, I mentioned fluorescence because ultrasound has a strong fluorescence. However, the EPO no. So we observed fluorescence painting, as you can observe here in the fluorescence intensity, fluorescence spectroscopy. When hybrid structure interact with singlet oxygen using methylene blue under red light irradiation, the fluorescence intensity decreases. And I evaluated different concentrations of methylene blue to understand the trapping process. So when I choose low concentration of methylene blue, after 48 hours, the fluorescence decay in 30%. And when I choose a large concentration of methylene blue, at the same time, the fluorescence decays to 70%, indicating that for large concentration of methylene blue, I process more EPO structure. And another interesting result is when I use low concentration of methylene blue for 10% painting, requires 2 hours, and for and I use a large concentration of methylene blue for the same 10% painting, I need 55 minutes. So this result suggesting that efficient and tunable singlet oxygen storage process. And after the formation, we evaluated the singlet oxygen release under X-ray radiation, and I used ESR spectroscopy, and you can observe in blue line for 1 and 3 ultrasound for loaded nanoparticle with singlet oxygen and X-ray radiation. We have an increase in ESR intensity in 30% in 50%, indicating these results that successive possibility of singlet oxygen release using X-ray radiation. And to understand how this could be possible, we proposed a mechanism. So classical approach to cycle reversion process use heat, UV light, or chemical activation. However, our ESR results show that X-ray radiation can also induce oxygen release. So a plausible explanation involves the emission of low energy electrons generated when X-ray interacts with both core. Electrons create a localized electron shower that excites ultrasonic peroxide layer and promotes CO bond cleavage and trigger singlet oxygen. This CO cleavage could be generate singlet oxygen or molecular oxygen, or other possibility is a OO cleavage. As a result, this results in ultrasound derivatives without extra oxygen release. Important to mention here, for our experiments, I just mentioned singlet oxygen release. So future investigation is necessary to evaluate the molecular oxygen release or even ultrasound derivatives. And to understand how both core act, I performed the ESR spectroscopy for bare ultrasound particle without cold core in loaded and non-loaded conditions, both X-ray irradiated. And as you can observe, we have a minimal increase in ESR intensity. So this result suggesting that X-ray amounts are insufficient to induce significant cycle-reversion process in bare ultrasound particles. So hybrid core shell structure is essential, where metallic core acts as an energy mediator and convert X-ray energy into localized electronic station that triggers singlet oxygen. And here is toxicity experiment for both systems. So I evaluated MTT assays Here I used A549 cells, but I changed I used two different ultrasound concentrations. For both with one ultrasound, for both loaded and non-loaded nanoparticles, I observed high viability until 0.1 milligram per ml of nanoparticles. And observe difference between the loaded and non-loaded nanoparticles, indicating that singlet oxygen remains stable and trapped in structure. In contrast, for both with 3%, I observed increase increase in toxicity and a significant difference between the non-loaded loaded nanoparticles. So these results suggesting that in loaded nanoparticles we could observe a spontaneous singlet oxygen release. However, I need to investigate more, and from these results, I chose to perform the in radiosensitization experiment using chronogenic assays, both with 1%. And here is the results of cells uptake studies. So absorbance measurements show a maximum internalizations happens after 3 hours, and the nanoparticles are localized in cytoplasma with minimal nuclear appearance. And the chronogenic assays shows that cells treated with singlet oxygen loaded, this blue line, uh, singlet oxygen loaded with gold and ultrasound nanoparticles and irradiated shows the significant low survival fractions compared to the both controls. So this results suggesting that X-ray trigger oxygen release translates into the enhanced radiobiological effects. And because of time, I will not present full detail of characterization of silver system. Instead, I would like to focus in these specific results for singlet oxygen generation, singlet oxygen detection of hybrid structures, because I observed the layer release profile. So immediately after X-ray radiation, both loaded and non-loaded nanoparticle present similar ESR intensity. However, after 96 hours post X-ray radiation, we observed a progressive increase in ESR intensity, and in 96 hours, we observed a threefold increase in ESR intensity. So this result is different compared to the old systems where I observed immediately oxygen release. And possible explanation of these different results could be related with atomic number of silver and the gold, with silver nanoparticle has a lower atomic number, which may result in reduced secondary electron generation and less efficient immediate activation. However, this system, silver system, could be applied to prolonged therapeutic effect, with singlet oxygen continues to be released even after treatment. However, this system could be these mechanisms to require future investigations. And I performed MTT system, but I didn't have to perform chronologic assays. So I'd like to perform this in futures. And the partial conclusion of these two approaches successfully synthesize gold with anthracite, silver with anthracite hybrid nanoparticles. For ESR spectroscopy, we observed X-ray induced singlet oxygen for gold is immediately, and for silver, we observed time-dependent singlet oxygen release behavior. And the gold system showed biocompatibility and clonogenic assays showed low survival after irradiation with singlet oxygen-loaded nanoparticles. And to finally, I'd like to present an innovative discussion of this two approach using radiobiological analysis. For this, I use a linear quadratic model where cell survival is described as an exponential function of the doses, and alpha parameter represents single event lethal damage, and beta parameter represents accumulated sublethal damage. And another parameter was dose enhancement factor, or DEF. For this, I compared the dose required to reach the same survival fraction with and without nanoparticles, and finally sensitizing enhancement ratio, or SER parameter. Here, SER is calculated using total area of survival fraction for control and the nanoparticles. And SER parameter evaluated the global radiosensitization process. And here is the results of these parameters. Start with GBF. For GBF with methylenol treated cells, and I evaluated these parameters. I observed an increase in alpha parameters and a strong increase in beta parameters. So these results suggesting that the indirect cross-mediated damage with multiple sublethal lesions. If radiosensitization were mainly due to increased production of secondary electrons from the high atomic number core, I expect more increase in alpha parameter. However, our data suggesting that the ROS-mediated multi-event damage predominates. So this result is aligned with scintillation. It has scintillated-mediated X-ray activated photodynamic therapy with singlet oxygen productions, where singlet oxygen promotes oxidative stress, affects not only DNA but also nucleobases, proteins, and mitochondria, and amplifying lesions, interactions, and apoptotic signs. And I observed highest SER value and the depth parameter increase with doses. And the next system, singlet loaded gold hybrid nanoparticles shows increase in alpha parameters, and the beta parameters remains unchanged. So this preferential amplification, this radiobiologic signature suggesting that enhancement of single event lethal damage and aligns with oxygen fixation hypothesis. In many papers, was reported improves in oxygen availability during the X-ray radiations, improves alpha parameters, and our system, we believe that singlet oxygen release under X-ray radiation. So we have rapid oxygen availability during the X-ray radiation. And I observed increasing depth in SER parameter, and the depth parameters increase most significantly at 2 bases. And here is a comparison between the two approaches. So for GDF nanoparticles, I observed highest SER value and the depth increase with doses. This indicating strong synergy with high dose irradiation, making it particularly suitable for hypofractionated treatments such as radioterapia. In contrast, for gold system, I observed modest increase in SER parameters and maximum depth occurring at 2 grays, which corresponds to the standard doses used in conventional fractionated radiotherapy. So this gold system could be applied to improve efficacy of standard daily radiotherapy treatment without increase delivered dose. So finally, here is a conclusion of this work. I successfully synthesized three nanosystems with distinct and complementary radiosensitization mechanisms. For using true strategy, one of them is scintillation mediated XPT with real-time singlet oxygen generation, and another is endoperoxide-based oxygen delivery with X-ray triggered singlet oxygen release. And these two approaches shows their different radiobiological parameters. GDF increased beta parameters, amplify rod-mediated lesions interaction, and GDF showed highest global radiosensitization. And the gold system increases our parameter with reinforced damage, fixation through radiation synchronized oxygen release, and the GDFs showed clinical relevant depth increase at 2 grade, that most relevant dose in conventional fractionated radiotherapy. So as a perspective of this work, I'd like to validate in 3D hypox tumor models performed in vivo biodistribution and safety study, model and my singlet oxygen release. However, this work shows that controlling where, when, and how oxygen is delivered may represent a promising strategy to overcome radiotherapy limitations. And finally, I'd like to take a moment to express my deepest gratitude to everyone who has been part of this journey. So first, I'd like to thank my supervisor, Professor Eder, to trust me and to continue support throughout my PhD. Your mentorship was fundamental not only for this work, but also for my growth as a researcher. I also sincere thanks to the committee members for being here today, for the time and for available contributions. To my colleague and collaborators, especially the Nanodose group, thank you for all support, the discussion, and moments we shared. I'd like to express a very special thanks for the care and the kindness you showed during my pregnancies. This journey would not have been the same without you. And I'm so also deeply grateful for all funding foundations for the financial support that made this research possible. And finally, to my family, the most important part of everything, especially my husband, Thiago. Thank you for being by my side for in every moment, for your patience and your constant encouragement. And my daughter, Olivia, she is my motivation. Everything I have done and achieved here carries a part of her. So finally, thank you all very much for your attention. Yeah, this.
Thank you, Mileni, for your presentation. Now we're gonna proceed to examination phase. So as you could note, the Mileni's thesis is related to several research areas, science areas, right? So we had to learn a lot about radiation ecology, about photochemistry, and organize all of this into a nanotechnology and medical physics perspective. So that's why we have 3 reference names in each of these areas, right? Radiation oncology, medical physics, and photochemistry. So to organize the examination process, I thought about following the alphabetical order. So that's why I invited Professor Mauricio Batista to begin the examination. So thank you all once again for accepting participating in this committee.
Okay. Do you hear me well?
Yes.
So first of all, I want to thank you to suggest my name. Very interesting work. Congratulations, Eder and Mileni, for this very nice work. And Mileni, uh, you did such a broad spectrum of things, went from the basics of understanding the photophysics, the photochemistry, the construction of the particles until the application in radiometric units. So this is really amazing work. Congratulations. You both produce very nice piece of work, and so I'm very happy to be here. And it's a time to congratulate, to I mean, we all to like this type of work that has such a level. So I'm here to party together, uh, and also to discuss, especially with Mileni, because I don't know if I'll ever have the opportunity again to have to in-depth discussion of this data. So that's the idea here. So without further delay, I'd like to ask you, Milena, to go to any of these schemes that you represent the photodynamic oxidation. We can start perhaps with page 46. So I use the, would you like to put this screen, or
Yeah.
people are following, or how?
Yeah, maybe you could share your thesis here, Mileni,
Okay.
so we can go all together.
So in page 46, are you sharing the thesis, or?
I think you should
Yeah, I'm trying to.
minimize this screen. You're right.
I'm trying to open because I have easily. I'm opening my computer.
Okay.
See?
Yes.
46. Here?
Yes. So let's start with the Jablonski diagram,
Yes.
and then my question relates to this electrons, the biomolecules, and then you end up with hydroxy radical, hydrogen peroxide, superoxide. So I wonder where this comes from. So this is a basic question. I want to discuss with you basic aspects of photosensitized oxidation. Okay, this is just a conversation. So I just wonder if you have considered where this comes from, this species.
For example, in
You can do any photosensitizer. You can think of anything that makes a triplet. From the triplet excited state, how do you get to this species?
I think probably from the cells inside of the molecular inside of the cells. I don't know, some proteins.
Yeah, so most people, because this is the way the community still thinks, most of the community, and I don't know if this will ever change. But anyways, this is connected to the work we have done in the lab for many years, decades, in which we have shown that actually the production of these species not really what matters for the damage induced by type 1. And actually what matters is the contact between these biomolecules and the triplet. And then you oxidize a lipid on this. You take it because you form here species that comes from the abstraction of electron or hydrogen from biomolecules. And then if this biomolecule is a lipid that is in the internal membrane of mitochondria, you damage 1 or 2 or 3 lipids, and then you are done. The mitochondria will produce catalytically a lot of it. So actually, it doesn't matter the production directly from this. It matters much more the damage these reactions cause in the biomolecules and the consequence to the cells. So, but this is, I always, because this is some work that we have done, others have done as well. But we trust this is the truth, but it doesn't mean that many people believe this. Still, on every thesis I go, I discuss this aspect. So I'm not bothered by the fact that you are reproducing the literature, which is there, I know. But I would like to know if you know where this comes from. And then when you get to know where this comes from, the reality is it's much more important, the damage this type 1 reaction causing the biomolecule than this direct production of these species, because I don't know if you understood what I said, Mileni.
Yeah, so you mean that the direct damage that the triplet state causes in the mitochondria or membranes, they are much more intense and significant in cell killing than the
yes, because then you have an organelle or molecule that is catalytically producing this. So if the organelle is not working, especially mitochondria, others as well, if you damage lysosome, you no longer have autophagy working well. And this produces a lot of radical species, a lot.
But
and then if you, the same in mitochondria, you increase the level of production of these species by the damage you cause in the lipids in the membrane, much more than what is produced directly. So this is.
Is there any textbook that has adopted this kind of new interpretation of the?
Well, actually, this is actually nothing of this is in textbooks. But if you look at recent literature. It brings this. We have few reviews and we are cited, but I don't. Yes, that's all I can tell you. I mean, and also I'm ready to discuss. If you disagree with me, I'm open to go ahead and discuss this. But this is what we observe in the years behind of research. So let's go then for perhaps. I would like to go now for page 9.
I'd like to ask it here, but energy transfer to generate singlet oxygen.
Yeah, this is type 2, and this is this is also important because singlet oxygen is a diffuse species, so it's going everywhere and it's causing damage also in mitochondria and other things. So it's flagging the damage, and this is starting to oxidize also lipids in the internal membrane of mitochondria. In the end, it's the same. You have a mitochondria that is not working properly, and this is killing to the cell.
Okay, thank you.
So it's just, of course, if you load your cell with a lot of photosensitizer, you start to see direct effects of the ROS produced by the photosensitizer. It depends on how much you put. But in conditions that we want really to understand what happens in cells under conditions of normal applications in which you don't have such a big load of compounds, and then you start to realize this, that this is just a turnkey that will make the cell produce a lot of damage and kill itself many times. And so if you can go to page 909, and this is related to this, yes, I'd like to discuss this because I understand the data, but as a scientist, I have a different interpretation. And then I want to put my interpretation on this, and then see how you respond. And this is how science works. We have to debate and we have to. So first of all, this if you look at this data that are presented in graphic H, this is absorption spectrum, right?
Okay, yeah.
And then we quickly realize that 4B, 6B, you have a lot more of dimers, as you pointed in the text.
Yeah.
But there is something else here that I would like to point. If this is normalized, right? This is normalized absorption.
Yes.
You normalize the whole thing to 1, right?
Yeah. Yes.
And what is the real absorption there? How much is the real absorption of this? I mean, because if you're measuring consequence of light absorption, and you load your system with a lot of absorption, you start to see things connected to the first layers of absorption. Not necessarily the photon will go through this, depending on how much light absorption you have. So let's go for the next slide then.
You mean the next figure?
The next figure, apologize.
Okay.
This one. Yeah, so this one, you interpret it as the following. So gadolinium nanoparticle that has covered by methylene blue doesn't have the traditional emission, right? Because you see there is a gadolinium emission there, but then you interpreted this as the light was reabsorbed by the methylene blues, right? And then that's why. But if you have a lot of methylene blue in the surface, the light can be absorbed by methylene blue that is dimerized or trimerized. And this, what happens is, this will have a very quick internal conversion. You cite our paper here, so I saw that you know some of the papers we published with methylene blue. And this will produce decreasing fluorescence. And also, I'm still wondering here if there is a proof that the light, the X-ray that is absorbed by the gadolinium will end up really exciting methylene blue. This is something I'm a bit puzzled. That's why I would like to discuss this point here. So I'm a bit concerned with this effect that a lot of methylene blue is stuck on the surface, and we are measuring here the photophysics of this.
So I didn't get your question.
Yeah.
So
because
you
once you have a thick film of methylene blue, we actually don't know how much light is propagating to the inside of the nanoparticle to come back as an excitation photon. As you mentioned, right? You have overlap of absorption of methylene blue and emission of the nanoparticle. Then if you excite the nanoparticle, there is a chance, a probability, as you discussed, that the light that you'll be exciting this will end up coming back as a methylene blue excitation. But I'm questioning if this thick film of methylene blue is the absorber itself of this energy. And then you have emission coming out from methylene blue that is normal from, if I get I have done some of these experiments, if I have a thin film of methylene blue, I excite this by any wavelength, I will not have a very quick emission like this, but this is more like internal.
But even if you are not exciting in the methylene blue excitation region?
That's why I wonder, since it's a very thin film, that's why I think there is perhaps another control here.
Yeah, because in this
with
case,
a very thin nanoparticle that does not have gadolinium on it, silica, for instance. You make the same experiment with silica and see how it goes.
Okay.
So this is a proposal for a new control, but that's all. I mean, I don't have the answer, but as a person that is working on this for some years, I I asked myself if this could be the thin film of methylene blue that is doing the job. So, but you can disprove this hypothesis by doing this experiment with a thin film of methylene blue that doesn't have the gadolinium inside, and see how does it do.
Yeah. Okay.
So you mean in terms of singlet oxygen generation?
No, this the emission that you're measuring here.
Mm-hmm.
This is because you're saying here by this data that the thin film of methylene blue is suppressing the emission of gadolinium, right?
Of europium.
Of europium,
Yeah.
sorry, of the europium.
Yes.
Yes. So in this case, we excited the europium directly at 396, and we looked to his emission at, I don't remember, but 60 something, 6014, I guess. And then we measured the lifetime.
Yes.
In the graphic A. In the B, we measured the energy transfer efficiency using the lifetimes and using the whole radioluminescence spectrum.
Using it here.
Yeah, using this here, yeah. Because you see the quenching of the scintillation emission, the radioluminescence emission.
Yes, exactly. This is one. It's the same thing here.
Mm-hmm.
I asked myself it. I guess with the scintillation. Well, yeah. If you cover methylene, yeah. So yeah, in this 1B, 2B, 4B, and 6B, there is no europium, right?
No.
Now, in every region spectrum has a europium.
Yeah, so
Here I just covered with methylene blue several times, and I observed this radioluminescence decay.
yeah, my observation it served also for this F and also for the other one, because the other one is lifetime. It's easier to discuss, but it's the same. I mean, we have emission that is suppressed by methylene blue film.
Yes.
But this not necessarily means that the emission from the europium will went to methylene blue. It could be that there is no excitation under this condition because there is a thick film of methylene blue that is interacting with this excitation that we don't know exactly how. So that's why I propose if you do a silica nanoparticle that is covered full of methylene blue, if you do have the same signal here, if you do have that, it's a proof that not necessarily this is happening. It doesn't mean that doesn't happen as well, but this signal is the excitation of the film of methylene blue that we don't know well how it behaves because it's no longer methylene blue, it's a stacking. So that's something I suggest in order to another proof of this or test this hypothesis that I'm adding to you would be a possible experiment. But anyway, it's up to you. It's just a suggestion here. Now, if you can find, I don't know the number here, the data connected to single oxygen emission. I forgot the page here. It's a little bit below here.
This?
Yes. Yeah, that's because one thing that I would like to suggest as well, we have here in chemistry one of the best facilities in the world to measure single oxygen emission, which without any question, because when you use probes, these probes are very difficult to be precise what they are measuring actually, because there are many reactions that could happen and having a specific response. But then we have the equipment here and it's open to you. Just bring the samples and measure. There is technician help as well. So I don't need to participate on this, but this is also good for your work because we measure the physical method of generating single oxygen, and I think it will help because I do not understand here, for instance, this ESR signal of the without any X-ray. It's not so small, right? We have and why is this?
Yeah, this is a good point. When I used this, I performed this experiment in water solution. When I perform this in ethanol solution, for example, I don't have this signal in without X-ray radiation. So I think when trans, I put in water solution, maybe having some oxidative response and cause this ESR.
Yeah, that's why I think it would be nice for you as well to develop the technology, measure single oxygen. Come here and measure it. It's open.
But I can incorporate X-ray in this because I mentioned single oxygen under X-ray.
Yeah, you need to bring some. I don't have a source. Can you bring a source or not? No.
Yeah, no, the problem is that I actually talking for almost 2 years with one guy that works with you in São Paulo, I forgot his name. But about buying a pulsed X-ray, because the problem is that we need a pulsed X-ray and the pulse should be nanoseconds or lower than that. And this is quite expensive.
No, you don't need that.
No?
No, we can make steady state. No, like a fluorescence spectra, you can measure emission of neurons. You don't need focus. You can shopper the sun.
Do you have the shopper?
Oh yeah.
Because then, in that case, we could. I have a portable X-ray. So
yeah, you should consider this because I think it's a way to help you drive in the right direction, measure single oxygen directly by near-infrared emission. The equipment is here. We have several equipments actually, so you can set up your system and stay for some time measuring on yourself. This is possible. I mean, you bring many samples, you put X-ray with shopper locking and something. We develop the equipment and then you measure many samples.
That's great. That would be great.
Please use it. Fantastic is paying for this, and my role is to advertise them. Yes, I think it's going to be very good for you for your research to do this.
For sure.
Another thing I would like to know: have you measured control of release of methylene blue from these particles? Because methylene blue is absorbed. I mean, when you put in ethanol, maybe everything is released. Or if in water it stays more, but perhaps it's released slowly. So do you have any measurement of this?
You mean mention the ESR spectroscopy using methylene blue solution and X-ray interpretation?
You put your nanoparticle solution, suspension, you let it rotate, and then you centrifuge and measure how much methylene blue is in solution.
Yeah, I mentioned this. You mean during the coverage process or in this?
In the final particles.
Yeah, in the final particles. In this coverage process, I wash the nanoparticles with water. I didn't detail. I don't know in the details, and I didn't detail in presentation. But for coverage process, I wash every time in the coverage process. And when I interact with PAA, then I wash with water, and then when I mix with methylene, I wash with water, and I observe it. I have a little.
Detaching.
Yeah, in this process.
Yeah, this is something you also have to consider, Mileni, because your particle may release methylene blue. and then you have two mechanisms involved. You have the photosensitization of methylene blue that's released, and then the methylene blue that's in the particle, and then I think it's not easy to stop the release of methylene blue. And I know because I did some thesis before and you watched many times, but then in the end we had a control to see how much it released, because it always released something. At least we know how much. So for the control for these cell studies, it would be nice if you know how much was released in the presence of any perhaps media or something, and then you leave it staying there for 2 days or something, and then centrifuge and see how much it was released. So I think this is a nice control as well for the system.
And we think one time to last coverage was PAA, but we didn't try this. The last coverage was methylene blue. Maybe if the last coverage of PAA, maybe this release process could be decreased. I don't know. I need to explore this.
Yeah, so I think the main messages I would like to exchange with you, I already did, so I'm not going to repeat similar questions with the other systems. I think it's you can measure single oxygen, it's here for you. In the system that you have anthracene, I think is very smart, very intelligent nanoparticle. I think you had very clear data that you are loading with single oxygen, but also I think you need more controls for the release.
Okay.
So I suggest you do thermal exposure of these particles, because the anthracene, when it's warming up a little bit, it releases single oxygen.
Yeah.
And also come here and measure directly. It's a very nice comparison, because you always do EPR, and there is benefits and side effects, and so if you do both EPR and near infrared emission, you are much safer in the conclusions. So again, the suggestion is the same. And so I finish here thanking and congratulating you both and the other members for the rest of the thesis. I'm sure there will be nice discussions here. So thank you so much.
Thank you very much, Mauricio, for your insight and suggestion. We definitely will follow them and try to add these new controls. And for sure, we're gonna bother you to go and measure this singlet oxygen species. So thank you once again. So now, following with the examination phase, I will pass the talk to Professor Roger to give his contributions.
Thank you, Eder. Good afternoon, everyone. Thank you, Eder and Mileni, for the opportunity to be here and know more about what you were doing. I think I first met Eder some 4 to 5 years ago. I'm not sure. And I'm really glad to see how much you've done, Mileni. Great work. I mean, it's congratulations. I'm learning a lot, and if you allow, I'll be sharing your thesis with people in my laboratory, or working also with the aspects of radiation and desensitization. I really enjoy reading your work. I try to decipher a little bit. I'm not a chemist myself, but I really enjoy to see what you've done. Let me, if I may. So when we think in terms of cancer treatment, you mentioned the surgery, you mentioned chemotherapy, and you mentioned radiotherapy. Now, more today, more and more we are understanding the strength of radiotherapy. But let me discuss with you a result which is in the literature, and see. I would like to see your interpretation. Okay. Um, so the authors irradiated cells and irradiated tumors in animals, and could show that irradiation did their work in terms of generation of oxygen species, lesions in DNA, H2X way high, and in one set of animals, radiation did work well, and the tumor shrunk. In the other animal set, they observed the same things. Radiation worked. You had an increase in local release of oxygen species. You have DNA damage, but the tumor did not shrink. Okay. What are the differences between the two animals? In one, in the sense that it worked well, the animals were immunocompetent, and the fact that radiotherapy did not work, uh, what happened there was a deficiency in type 1 interferon receptors. So everything happened as the radiobiologist would say it would happen, but the result wasn't there, right? So, did you know this experiment? So, what do you feel about that? I mean, you have all radiobiological features, check, check, check. But then when you look at was radiation effective? Radiation was not effective. That's the tumor shrinkage. Radiobiologically, it was perfect. But for the
translates to.
yeah. How do you feel about that?
Yeah, this is yeah, yeah, it's pathetic. Uh, I don't know. I think um, we we think about this system, of course, to produce to has an effective biological response.
Okay.
However, I know when we translate to the to in vivo experiment, I didn't do this.
Right.
I did using my nanoparticles. I just we have the clinical experiments, and I know I have a name. I found a name.
I mean, I want to discuss research with you. Okay. I mean, your work. I can tell you that I think you are a very, very strong candidate for the PhD. I think, in my opinion, you got the PhD already. Okay. So I'm talking with Dr. Mileni.
Thank you.
Okay. So and, I just want to illustrate something. So radiation will work in immunocompetent animals, but not in efficient animals that do not have that one responses, right? And as we started digging up, I mean, as people in the literature start to dig up, what are the causes? They came to the conclusion that release of nucleic acids from mitochondria would, upon radiation, would be critically important to promote this type 1 interferon response. And you would not have radiation therapy effective if you don't have immunity, right?
Mhm.
Nowadays, immunotherapy is a fourth pillar for cancer treatment,
Yeah.
right? So besides surgery, immunotherapy,
Mm-hmm. Yeah.
chemo and radio, we
Mm-hmm.
have immunotherapy, and radiation seems a very potent way of triggering immunity.
Mm-hmm.
And so, if you learn how to release nucleic acids from mitochondria, for example, even if the doses are not huge, you can eventually promote the effects, attack one effector response, and you can
Mm-hmm.
be effective, right? So in that regard, I think the approach that you and others are taking of collaboration of us and others is very smart because you can eventually deliver the nanoparticle you were working to a specific organelle, for example, to mitochondria.
Yeah.
Have you thought of doing this? And I mean, can you elaborate?
Mm-hmm.
How would you do it? Can you increase, for example, or gadolinium nanoparticles or gold nanoparticles in the mitochondrial subcompartment? So,
To guide them to the mitochondria, you
yeah,
mean?
and then have what Mauricio just suggested. So, if you have some molecules in the mitochondria that are damaged, then you can really amplify the effect, the
Radiation.
biological effect, because the mitochondria, to use a word that he need, will catalyze, right? If I understood correctly his argument.
Yeah, I've seen some works on a long time ago related to gold nanoparticles where they were trying to make them positive because I remember being positive they are more likely to attach to the mitochondria.
Okay.
So if that is true and is still used, I'm not sure about that. But in that case, methylene blue would help because it confers the nanoparticles a positive charge. But I mean, there are probably more smart ways to do this better than only using the surface charge, right?
Right. Right.
I don't know if any other one knows.
If I understand correctly, it's better to attach nanoparticles in mitochondria than nucleo, for example.
Yeah.
In
Yeah.
for okay, so we could change the surface of our nanoparticles to active targeting mitochondria, for
Mitochondria
example.
stand up nuclear.
Now, this is, I think it's interesting to think about it and
Mm-hmm.
see if there is a way of partitioning the nanoparticles to
Mm-hmm.
specific organelle, right? So you could eventually enhance the local effect. So I was in I had a similar question that Maurice already did about methylene blue. So, if I'm not wrong, albumin is a very potent binder of methylene blue, right? Isn't it?
Who?
Albumin.
Albumin, like DSA, for example, it would bind methylene blue. I mean, you can,
Oh, the albumin, the
yeah.
protein.
So, what happens with what's the stability of your compound when you add that to zero, which is rich in albumin? So the next will be stability of your methylene blue.
I guess you tested, right, Mileni?
I think I test
The
for
stability.
old system. I don't know if I test to GDF system. For old system, I test. Yeah, here, here is for both GDF system.
And the medium, right?
Okay, but what PMI medium? Do you have serum, bovine serum? Or I understand our PMI medium just as the medium.
It was the rich medium, like with the bovine serum.
Yeah, I think it is.
I don't remember.
Remember, but I think the medium with and I think the medium with 10% heat impact that fit above serum.
Oh, okay.
1%. Yeah, I think it's.
Okay, so it's the complete medium with. Okay.
Yeah.
Okay. There's it's I think it's jargon from the areas. For me, our PMI medium is only the medium. Then you add things on, right? Okay. Okay. So did you measure the stability then of the particle in the medium?
No, I just measured the hydrodynamic size. I didn't measure the stability with the time.
Okay, because this would promote the diffusion of methylene blue.
Okay, yeah.
Methylene blue.
Mm-hmm.
If I'm not wrong. So, and you showed somehow that there is cytotoxicity that is independent of irradiation, which is not manageable in my opinion, but it's controlled. Do you know what's the mechanism of cytotoxicity of the particles? Do you have any suggestion?
Sorry, which was the question? I was.
The mechanism of cytotoxicity of nanoparticles without its realization in our MCT assays. When I increase concentration, I observe increasing viability.
Decreasing.
In the harm mechanism to cause this. Maybe when increase concentration, the cells.
So, please tell me if you are not, if this is not a problem for you. Please tell me, because I come from in the biological setting. I would be worried about that, but eventually this is not an issue at all. I want to hear your opinion.
So for all the nanoparticles, you mean? For both?
Yeah, you have you tend to have some more than the others. The gadolinium, for the gadolinium, that's more present. If I'm not wrong, I think it's if you go. Can you show the figure?
The MTT for gadolinium.
Yeah. So you see the gadolinium, europium, and then you start to have with a concentration of 125 milligrams per ml. You have around 6% of cytotoxicity. Is this okay for you? Because it would be if it's only radiosensitization, for me this would be a no-go. But if it's only radiosensitization that you want, right? So, but I mean, honestly, I wanna understand it from you. This may be okay if you can have a control released in vivo. This could be okay. I'm trying. We used to extrapolate in vitro,
Yeah.
profound in vitro,
Mhm.
and this would be in the premises that we accept. This would be a no go. But I understand that that was the goal for you, right? Because you use this, right?
Yeah, yeah, I use this. I think for translate in vivo maybe could be a problem.
Okay.
However, for radiosensitization, for using clonogenic assays, I use this lowest concentration of methylene of the nanoparticles,
Right.
and using this low concentration of the nanoparticles, I can observe this radiosensitization process. So I think if uh, maybe I covered these nanoparticles with something normal biocompatibles
Okay.
and improve the viability to translate in vivo experiments.
I see.
Uh, yeah, maybe this. But I think with these results to translate in vivo, maybe
Okay.
it's not work. It can be cause some damage.
Right. Right. I got it. I got it. Because one of the issues that will be time, not in your thesis, obviously, but it should be toxicity of gadolinium. I mean, gadolinium is toxic. If it builds up in the body,
Mm-hmm.
it's toxic. Gold is less toxic. Silver is toxic. So
Yeah.
we are planning to use silver nanoclusters for radiosensitization.
Mm-hmm.
That we are aware. I mean, we can't see toxicity. I mean, this is an issue, right? That we need to tackle. It to be we need to balance it, right? Uh, the
The benefit should be higher than the risk, right?
yeah,
But I think in terms for without X-ray radiation, for example, using GDF with methylene blue is a similar
yeah,
color deformation with
right.
control without any treatment.
Yeah, I got it. I got it. So this is good. Although the time frame here is different, right?
Mhm.
The time frame of the experiments is different, right?
Yeah.
So,
Yeah, yeah. Here is 40,
I guess 48.
should be
48,
hours.
48 hours, and here is at 10 at
Yeah.
15 days.
Okay. Okay. Awesome. Okay.
It's interesting that the ones covered with metal and blue seems to be less toxic than the DDF, the bare DDF, right?
Okay. Yeah. That's interesting, right?
In hypernized
Yeah.
with methylene blue has present more.
Right. But in graph B you have the opposite, right?
Yeah, in graph B. But here is the another cells. Here is murine.
Yeah. 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 It's mind-boggling. I mean, we need to understand that. Honestly, if I were to set a limit, and I'd like to listen more from you about that, I would not use anything that is at an MTT level would be more than 10% cytotoxic at first, if the aim is radiosensitization, right?
More, nothing more than 10? So you mean viability above 90?
Yes.
Okay.
Yeah. I mean, this is. I would establish this as a threshold in the beginning and try to work in the delivery method so we can spare cells because you should imagine that non-tumor cells will be exposed to that as well, right?
Yes.
In vivo, right?
Mm-hmm.
So unless there is a way of delivering only to cancer cells, then that's great because you have uh, the cytotoxic effect of the molecule, and in addition, you would also have the radiosensitization. But in reality, we do not have that precision, right? Not in the system as you are designing right now, right? It will get into every cell, in principle, right? Okay.
Yeah, we actually established 80% now for these experiments. Yeah. That's why we use the lowest concentration of DDF, not because the covered one,
Yeah.
but because the bare DDF was more toxic, and we wanted to have them as control, right?
Yeah.
So that's we limit that. Looks like maybe if you don't want to use the GDF as control, we could use higher concentration, right? Because even the 0.125 is above 9%.
Right.
Yeah. But we need the controls, right?
Cool. Cool. Very good. And could you walk me through your alpha and beta calculations? I'd like to understand myself. And it was very nicely presented. Could you walk me through just for my understanding? How did you calculate the beta practically?
You mean, sorry.
For which parameter? For which model?
Any of them. I mean, you do the radiobiology, you do a single insult, you calculate the alpha, and then for the beta, how do you establish that?
I used a program. I put the every value with survival fractions with the doses, and they returns to me alpha and beta factor. I used Prisma program. Using this survival fraction, this equation, exponential.
So, but then the beta was estimated from a specific measurement, or I'm not sure. I'm not sure I got the calculation here.
I have this graph,
Yeah.
graph B, and I calculate using this equation as an exponential of
Okay.
minus with alpha and beta parameters, and I did a regression. Regression.
Yeah,
Okay.
fitting.
Yeah, I fitting, and I take these parameters using these fittings.
But you did that in Prisma or in Origin? In the software?
In Prisma.
Prisma.
In Prisma software.
Okay. So you do not have an example of, I mean, you don't have a survival fraction of cells exposed to 4 times 2 grays.
Mm.
You have the cells exposed to 2 grays, 4 grays, 6 grays, and 8 grays.
Yeah.
Single exposure. Okay,
Yes.
I got it. Have you tried to do as we do in the clinics 2 4 2 plus 2 plus 2 plus 2?
No.
Okay.
In biological.
Different days. Okay.
That would be interesting.
I guess you have a different result there.
And we observe a difference in physical chemical experiments. When I use it, for example, for 8th grade, direct to 8th grade, or 2 and 2 and 2, we observe a difference in physical chemical response.
Right. I would be curious to see, for example, if there's a toxicity or so the cells have a compound, and then they're exposed to a single dose of 2 grays, or a single dose of 8 grays, and then repeated doses of 2 grays for 4 days.
Yeah.
Because then you have the repopulation taking place.
Yeah.
And I think you may see interesting biology there with your radiosensitizing compound.
Mm-hmm.
Does it make sense to you? And,
so your suggestion is to make multiple 2 grays fraction, right? To simulate the fraction radiation.
To mimic what we do in the clinics, right?
Yeah.
A fractionation,
Mm-hmm.
a fractionation regimen over a week. We do. We usually use for here at the hospital. We do lung cancer. Usually it's 3 grays every day for 5 days, then 2 days off. So we do the conventional fractionated therapy here. Right.
But in that case, are you using or testing any drug or nanoparticle?
Well, not in the patients.
Ah,
But
see.
Yes, in our
Cells.
research we do fractionate with drugs that we think may be either radiosensitize or change the repopulation phenotype.
And in that case, when you treat with the drug, like only the first day or every day before the doses?
If it's radiosensitization, right now the protocol we are running, we added the first day before starting radiation, and we simply keep adding, keep irradiating every day without
any new treatment,
without washout.
So the nanoparticles remains in.
Sorry.
The nanoparticles remains in.
Yes. So the nanoparticles are not washed out.
Okay.
But I mean, this is it's an option, right? I mean, once you establish it, you just need to be consistent, right?
Mm-hmm.
Okay. Cool. Very interesting. Well, it's awesome that we came together. If you want to do the experiments in organoids here, we can help you with that. If this is something we can do the 3D models.
Mm-hmm.
Eventually we can, if that works well, we can then go to patient-derived organoids. So we could add something if this is the case. How do you imagine that the compound will get into the tissue, diffuse into a 3D structure? For 2D structure, I mean it's clear, but for 3D.
Yeah, I think for GD, for gold system, where have a small nanoparticles, the hybrid nanoparticle has a size below 10 nanometer. I think probably diffusion is more happens in tumor, but for gadolinium, I don't know. Maybe I don't know.
It would be interesting to do the experiment and check what's the diffusion rate.
Yeah.
Okay.
Could you simulate hypoxia in the organoids?
Absolutely, yes, it is. I mean, the organoids already they have a hypoxic sensor.
Wow.
Mm-hmm.
So one more to bother next week.
So whenever you come to do the experiments, the oxygen with oxygens with Mauricio, you can come on that. So
yeah, that's true.
Cool. Thank you and congratulations, Dr. Isikawa. Very, very good work. Congratulations, then.
Thank you.
So thank you very much once again, Professor Roger. Very nice point of view and suggestions. We'll definitely follow them for sure. And now proceeding with the examination, I'm going to invite Professor Ross to give his contribution. I know Ross has contributed a lot since Mileni started her PhD, right? But maybe there's still some new suggestions and, and point of view.
So thank you, thank you very much, Eder, and thank you, Mileni, for the opportunity to be here today, to participate in this and to celebrate your achievements. Yes, I've seen some of this work up close, did some of the work in our laboratory here. You and Eder both received funding, really impressive funding to come here to Boston to do some of this work, and so congratulations for that. It's so great to see it all together in one format like this. Really, really wonderful job. My questions are kind of general, not very specific. So to begin, in your talk, you mentioned the sizes of the nanoparticles, so something around 100 nanometers, kind of the final size of the nanoparticles. Yeah, I don't remember which one it was.
Gadolinium has a 100 nanometer, and gold and silver nanoparticles have 10 below the 10 nanometers.
So my question is, what's a good size for clinical translation? You know, what should we be shooting for?
I think the small size is better. So the gold system is better than the gadolinium. But I think if we cover it with some things in this gadolinium system, maybe it could be improved in accumulation in tumor. But I don't know how this size, 100 nanometer, affects another the biodistribution.
So yes, why is
or in some organs, or they release for the body. I think silver and gold nanoparticle is released for body because the small size, but I don't know.
So is there? Yeah, I guess that's the question. Is there a threshold that we should be trying to get under? If smaller is better, how small is small enough? And there is an answer, I think, in the literature regarding bypassing the liver below a certain threshold. You don't have liver accumulation, and you can excrete through the kidneys, which is important for a clinical system. So there is a number, and you might not know the number. I'm just curious if you do.
For renal clearance, they usually say below 5 nanometers for a complete
10.
But then the point is we're gonna decrease a lot the circulating time, right? So the probability of being accumulating tumors will decrease as well. So that's
possibly.
Yeah,
and I think there's also some data on diffusion in the tumors, right? A certain size for diffusion in the tumors, as well as I've seen some data, and I forget what the number is, for internalization by cancer cells. People have cited certain numbers there. So many different things to weigh when engineering a nanoparticle to be used.
Yeah, there's a lot of stuff to research yet. Right?
Okay, so another question I had was about flash radiotherapy.
Yeah.
So you mentioned in your talk that flash radiotherapy would be appropriate for the gadolinium system and would be synergistic with that. Can you say more about that?
Yeah, this actually is now because I observed the rate of sensitizations increase with the dose. So I thinking about where when I use it more X-ray radiation, I produce more biological effect from the GDF system. So I think about the treatment with using a high energy, high X-ray energy deposition, and I think of flash therapy, but actually I don't know if work. Understand? Or
Yeah, I think, but for flash, it's not just about the total number of gray, for example, like the total dose. It's also about the time, right? So it's very fast.
yeah.
And the benefit of flash therapy is that you can overcome hypoxia with it, right?
Yeah.
And so that's why I'm wondering with these nanoparticles, what's the interaction, because you're generating these cross species. Is there an extra benefit there? Is there a problem? Like, do you have this like oxygen depletion situation because it's so fast? I'm very curious.
Yeah. So your question is about how fast would flash be related to the consumption of oxygen, right, by the photosynthesizer?
Yeah, how would that interact? What would be the interaction there? And I haven't thought it through. Like, okay, so flash is very fast, and so you have this oxygen depletion very quickly. Does that does that affect the reactive oxygen species generation? I don't know.
Yeah. What I was considering is that in the two systems Mileni tested, is actually that the ones able to release oxygen would benefit, because if the concentration of this nanoparticle is higher in the tumor, the depletion will take longer to happen, right? The oxygen depletion, because the health tissue will have oxygen depletion and the tumor as well, but the nanoparticle will release more. So here the damage will like take longer. However, for the ones with the photosensitizer, I think the depletion will happen faster in the tumor if the photosensitizer is in the tumor, because the excited photosensitizer will also consume the oxygen. And the oxygen, the molecular oxygen can diffuse, but the singlet oxygen is highly reactive, so it will react with something and be stuck, right? So I'm afraid that the ones with photosensitizer will not be good for flash, because there will be two things consuming oxygen, and
I see. So it'll become even more hypoxic.
yeah. So maybe it would be better to have the photosensitizer in the health tissue and not in the tumor, because then we're gonna reach the plateau faster. Yeah, but then we have the damage of the singlet oxygen. Yeah. And
That's interesting.
that's
Okay, so
something I
something
was
to think about.
considering. Yeah. Sorry?
Yeah, something to think about. Something to think about.
Yeah. It would be very not easy, but something like that we could test if we have the flash source, right?
Yeah. No, I think if we could come up with a hypothesis, that's something we could try to do here.
Yeah, that would be great.
with
Because
protons.
we have
Large
like kind of well-established or at least well-investigated platforms that works in different ways, and I think
Yeah.
they will contribute different when you have a flash beam,
I think
ultra
that's- I think
fast beam.
It's an interesting direction.
Yeah.
Okay. Another very taking a big step back, Mileni. So so you've been working in this field for many years now. You're an expert. You know, nanoparticles, nanochemistry, radiation oncology. So based on your experience, what's the best? What's going to be our best approach for cancer therapy? Like, if I were to give you, you know, you're now a PhD, and now you're going to be a faculty member and have your own lab, and then some rich person is going to come along and give you unlimited funds, $100 million, and say, Mileni, I'm giving you this money, solve cancer. Solve cancer. What would you do?
Honestly, I'd like to apply this money, for example, in using nanoparticles combined with immunotherapy. I think this is a way to solve cancer disease. So I think if I have this money and the knowledge, because I don't have knowledge in immunology, I'm trying to study now. No, in this.
The near future.
Yeah, but I think I would like to apply nanoparticles combined with therapy to. I think this.
So like nanoparticles with like some immunotherapy attached, or like nanoparticles and immunotherapy and radiation.
I think I try to combine everything: immunotherapy and nanoparticles and radiation, and try to see if this is best system or no.
That there's something there.
Yeah. I think I really satisfied with these results, with the collagen phase. We had a good results, but I don't know where this can be could translate to the in vivo or clinical condition, because I know the synthesis of these nanoparticles is not so easy. I try to synthesize. Actually, this synthesis is so
Reproducible.
Yeah.
Reproducible.
Yeah. Both GDF and the code system both is. However, when I translate to the industry, for example, I don't know how this is work. I produce in laboratory, so I don't know in the industry this is for this is possible or no. But I really like my nanoparticles, and I think this.
I think that's a good. I think it's good to be thinking that way.
Yeah.
About how would this translate to people? How would this scale up? Because ultimately that's what we're doing here, right?
Yeah.
Like it's fun science, but the point isn't the fun science. The point is to help people eventually.
Yeah.
And so we should always be thinking that, okay, you know, if there's a decision somewhere, okay, this is cool science, but this part would actually be easier for manufacturing, or, you know, might be more reproducible or more stable, or or less toxic. We need to be thinking about this as we do science, as we do medical science, right? This is medical science. To make sure that what we do is relevant for the future, and will eventually help people, because that's why we're doing this work. Not just because it's cool, right?
The main goal.
But it is cool. So I don't have any more questions. Very short.
Okay. Thank you, Ross.
Thank you.
Thank you once again. I'm sure we're gonna have more opportunities to collaborate in the near future, and to start think about this new hypothesis we all here have raised it, right? I think it was a very nice examination and discussion time here. So, well, that's my time to go for the examination process, but as an advisor, I think it's like I don't have any more question. Once I have had the opportunity to argue and ask and instigate Mileni since 2018. She's a big survival, and I'm a luck advisor. Once Mileni was my first master student, and now she's my first PhD student defended. And I think I'm really proud of the work she developed. And this is much of because of her dedication and love for her work as a researcher, right? So during master, Mileni had the pandemics to like make the things not work so well, but she did a great master work. And during the PhD, we had Olivia, right? But Mileni did a really great work, even having a pregnancy during her PhD, right? So I think this is a really big proof of his commitment and his dedication to his work. And yeah, so I only have to thank you, Mileni, for being part of my group. And the great news that Mileni is going to continue in the group, right? Because she was awarded of a PESP postdoctoral fellowship. So hopefully next year she will continue in our group. And so now we have reasons to try all the suggestions you all suggested, right? The committee suggested. So thank you once again, Mileni. Thank you, the committee. Now we're gonna have the committee members. We have to meet in a secret meeting. So I invited you guys already via email with another link. So I'm gonna pause this transmission, and you're gonna meet in another room. Let me know if you three received the email. I'm already in the other room, and so people watching in the YouTube can continue here, and Mileni can also continue in this room, because we're gonna move. I asked you three to leave this room or just stop transmitting audio and the screen. So Professor Roger is already here.
Sorry, where's the link for the new room?
I sent
what should I do?
You should enter. I sent in your email. Let me see.
The email. Okay.
Yeah, I sent a new link, a different link, so you can enter this link. Let me just check, Ross, which email I sent to you. I think it was the dfci.harvard. Have you received it? Did you receive it?
I got an email from you
with the thesis, but I sent an invitation for the for the room. Mauricio's here. Found it?
When was that? Was that today?
Yeah, like minutes ago. I'll send again. So which email you want me to send?
Oh, I got it.
You got it?
I got it. Okay. See if I can get it.
So.
All right, so I leave here.
Yeah, you can mute your microphone and stop your screen, and then you enter the other room. And then we'll talk in the other room. Estão me ouvindo?
Sim, ouço bem.
Só esperar o Rosa entrar aqui, então.
Legal.
Bom, não sei se aí no Instituto e na Faculdade de Medicina funciona da mesma forma, mas aqui a gente... Rosa entrou. Estão me ouvindo? Tô ouvindo. Só esperar o Rosa entrar aqui, então.
Legal.
Bom, não sei se aí Peraí, que tá dando um delay, né? Funciona da mesma forma, mas aqui a gente... Estão me ouvindo? Tô ouvindo. Acho que tá dando eco no microfone de alguém, será? Bom, não sei se aí Peraí, que tá dando um delay, né? Funciona da mesma forma, mas aqui a gente...
O outro precisa estar desligado também, será que é isso?
Acho que tá dando eco no microfone de alguém, será? Oi? So Mileni, after a hard time to decide in approving or not your PhD defense, all the three members of the committee have approved your defense. So congratulations, you are now a PhD from the University of São Paulo. So congratulations, Mileni. Would you like to say something?
I don't know.
No? Relief?
No, I just, yeah. I'm really happy. Thank you for your time. It's really thank you for your contribution and your time.
A lot of hard work. Congratulations. You've earned it.
Mileni, you were one of the few that can do being a mother and a PhD at the same time. So you deserve a congratulation to the third or fourth hour. Very much.
Yeah, that's true. Definitely true. So that's it. Thank you very much.
Congratulations to you as well, Eder. And never forget that you have a single option equipment to you here. You just have to use it.
Thank you very much. And please send me the information about the conference. I'm actually interested in going. We both, actually, my research group as well, a lot of people.
You need to be very fast because the deadline was last week, so I can arrange to fit you in, but let me know very soon, as soon as you can.
Okay. Thank you.
All right, we'll celebrate tonight.
Yes, you deserve. You both.
Okay. So thank you very much once again.
Bye.
Bye. See you soon.
Parabéns, Éder.
Obrigado, professor.
Obrigada, professor.